This naturally leads to a decrease in overall density. The observed density evolution provides a test for cosmological models. If the universe expands according to a certain metric, galaxies should evolve in a predictable way. If observations disagree with predictions, it suggests either the metric is wrong or galaxy evolution involves processes not included in current models. Some alternative cosmological models predict that distant galaxies should have similar sizes to local galaxies. In these models, the universe does not expand or expands in a different way. Redshift comes from motion through space rather than the expansion of space itself. These models are controversial and not accepted by mainstream astronomy, but the density measurements provide data that any model must explain. Whatever the explanation, Webb has revealed that galaxies in the early universe do not simply look like smaller versions of modern galaxies. They are fundamentally different in their structure and dynamics. Understanding this transformation is key to understanding how galaxies form and evolve, and the differences extend beyond just density. JWST should be dim. It sits more than 13 billion light-years away. Light from the galaxy has traveled across expanding space for most of cosmic history. By the time it reaches Webb, each photon has been redshifted, losing energy. The photon flux has also been diluted by the expansion. Distant objects always appear fainter than nearby ones. Yet JWST is bright, surprisingly bright. So bright that Webb could have detected it even if it were 10 times fainter. This raises an obvious question. If this bright galaxy is easy to find, where are all the other bright galaxies at similar distances? They should be everywhere. The answer is that they are everywhere. Webb has found numerous bright galaxies at high redshift, far more than predicted by pre-launch models. These galaxies dominate the early universe in a way that cosmologists did not anticipate. The universe at cosmic dawn was not dim and quiet. It was ablaze with star formation. Measuring a galaxy's brightness tells you about its star formation rate. Bright galaxies form stars rapidly. The ultraviolet light from young, hot stars makes the galaxy luminous. By measuring how bright a galaxy appears and correcting for distance and redshift, astronomers can estimate how many stars form per year. JWST forms stars at a prodigious rate. Estimates suggest dozens of solar masses of new stars per year. For comparison, the Milky Way currently forms about 1 or 2 solar masses of stars per year. JWST is tens of times more active, despite being much smaller. This high star formation rate, concentrated in a small volume, creates the observed brightness. The galaxy's size adds to the puzzle. At over 1,600 light-years in diameter, it is larger than expected for its age. Simulations predicted that galaxies at this epoch would be tiny, perhaps a few hundred light-years across. JWST is several times larger. It has had time to build substantial structure. What makes a galaxy bright is ultimately the number of young, massive stars it contains. These stars burn fiercely, emitting copious ultraviolet light. A galaxy with more young stars is brighter, so the brightness mystery reduces to a question about star formation. Why do early galaxies form stars so efficiently? One factor is gas supply. Galaxies in the early universe are gas-rich. They have not yet converted much of their gas into stars. With abundant fuel, star formation can proceed rapidly. The gas is also pristine, composed mostly of hydrogen and helium. It flows into the galaxy along cosmic web filaments, providing a steady supply. Another factor is the lack of heavy elements. In the modern universe, dust grains formed from heavy elements help cool gas clouds, facilitating star formation. But dust also absorbs ultraviolet light, dimming galaxies. Early universe galaxies have little dust, so their starlight escapes more easily. They appear brighter than a comparable nearby galaxy with more dust. Feedback mechanisms also differ in the early universe. In nearby galaxies, supernovae and black hole winds regulate star formation. They heat or expel gas, preventing it from collapsing to form new stars. Early galaxies might have weaker feedback because their black holes are still growing and supernovae are just beginning to enrich the interstellar medium. Weaker feedback allows star formation to proceed at higher rates. However, these explanations only partially resolve the brightness puzzle. Even accounting for high gas content and weak feedback, simulations struggle to produce galaxies as bright as observed. There is a gap between theory and observation. Either the simulations are missing key physics, or the observations require reinterpretation. Some researchers propose that the luminosity is temporarily boosted by a starburst phase. During a galaxy merger, or after a large influx of gas, star formation can surge to rates far above the average. These bursts last only a few tens of millions of years, but during that time the galaxy appears exceptionally bright. If we happen to observe galaxies during these brief, bright phases, they would appear more luminous than expected based on their long-term average star formation rate. Another possibility involves the stellar initial mass function, the distribution of stellar masses when stars form. In the local universe, most star formation produces low-mass stars, with fewer high-mass stars. If the early universe preferentially produced more high-mass stars, the total ultraviolet luminosity per unit mass of stars formed would be higher. This would make early galaxies appear brighter without requiring more total star formation. Testing these ideas requires detailed observations of many galaxies. Webb is conducting large surveys to build up statistics. By examining hundreds of early galaxies, astronomers can determine whether the bright objects are rare outliers or represent a typical population. Current data suggests they are typical. The early universe was genuinely brighter than models predicted. This has implications for reionization. Bright galaxies produce more ionizing photons. If the early universe contained more bright galaxies than expected, it produced more ionizing radiation. This could have reionized the universe faster than previous models suggested. Webb observations of reionization-era galaxies will test this idea. Meanwhile, on smaller scales, Webb found something extraordinary. Alpha Centauri is our closest stellar neighbor. 3 stars orbit each other just over 4 light-years from Earth. 2 of them, Alpha Centauri, A and B, resemble our home star. The third, Proxima Centauri, is a small red dwarf. This system has fascinated astronomers for decades. If there are planets around our nearest neighbors, we want to find them. Proxima Centauri hosts at least 2 confirmed planets. One orbits in the habitable zone, where liquid water could exist on a rocky surface. But Alpha Centauri, A and B, have been harder to search. They are bright stars, and their glare overwhelms the faint signals from any planets. Ground-based telescopes struggle to detect planets around such brilliant nearby stars. Webb changed the game. Using its mid-infrared instrument, astronomers devised a custom observing strategy to peer into the glare of Alpha Centauri A. They found something. A faint infrared source sits about twice Earth's distance from the star. The signal is consistent with a large planet, possibly a gas giant. This detection is tentative. Confirming it requires additional observations to rule out other explanations. The signal might come from background objects or instrumental artifacts. But if real, it represents our closest planetary neighbor outside the solar system, aside from Proxima's small worlds. Finding a planet at Alpha Centauri would be monumental. The star system is so close that future missions could potentially visit it. Detailed studies of any planets there would provide insights into planet formation and habitability in systems similar to ours. Even a cold gas giant would be valuable for understanding planetary system architecture. The observing technique developed for this detection demonstrates Webb's versatility. The telescope was designed to study the most distant galaxies, not bright nearby stars. Yet, with clever strategies, astronomers can use it for both. This expands Webb's scientific reach and ensures that surprising discoveries come from unexpected places. Alpha Centauri A is slightly larger and brighter than our home star. If a gas giant orbits there, It likely formed through core accretion, the same process that built Jupiter and Saturn. A solid core accumulates from colliding planetesimals, growing until its gravity becomes strong enough to pull in gas from the surrounding disk. This process requires millions of years and a disk with sufficient material. The potential planet orbits in the habitable zone, the region where temperatures allow liquid water. However, as a gas giant, it would not have a solid surface. But gas giants can have rocky moons. If this planet exists and hosts large moons, those moons might be habitable. This scenario mirrors Jupiter and Saturn's moon systems, where moons like Europa and Enceladus harbor subsurface oceans. Detecting the moons would require even more advanced telescopes than Webb. The moons would be incredibly faint, lost in the glare of both the star and the planet. Future missions dedicated to directly imaging exoplanets might have the capability. These missions would use star shades or coronagraphs to block the star's light, revealing the planets and potentially their moons. The Alpha Centauri system also serves as a test case for theories of planet formation. Our home star formed with certain properties, and the solar system has a specific architecture. By studying planets around similar stars, astronomers can determine which aspects of the solar system are typical and which are unusual. This context helps answer whether systems like ours are common or rare. If future observations confirm the planet, it will become a prime target for follow-up studies. Astronomers will measure its orbit precisely, determine its mass, and search for additional planets in the system. They will also look for signs of a debris disk, leftover material from planet formation that might still orbit the star. Webb's discovery potential extends far beyond distant galaxies. It is revealing the cosmos at all scales, from the most ancient structures to the planetary systems next door. Yet, even as it finds new worlds, it has also uncovered fine details in the space between stars. The space between stars contains more than just emptiness. Gas and dust fill the void, though at extremely low densities. In some regions, the material clumps together into molecular clouds, dense enough to collapse and form new stars. Between these clouds, thinner gas spreads throughout the galaxy. Webb's observations of the Cassiopeia light echo revealed that this interstellar material has intricate internal structure. Scientists measured features as small as 400 astronomical units across. These structures appear as tightly packed sheets, stacked like layers. The discovery changes our understanding of the interstellar medium's organization. Before Webb, astronomers viewed interstellar clouds as relatively smooth and featureless. They knew turbulence stirred the gas, creating some structure, but the details remained hidden. Webb's infrared vision combined with the light echo technique illuminated these structures for the first time. The sheets are real and ubiquitous. Magnetic fields likely sculpt the sheets. The interstellar medium is ionized in many regions, meaning atoms have lost electrons. Charged particles feel magnetic forces. As the gas moves, it drags magnetic field lines along. Over time, this interaction organizes the material into elongated structures aligned with the field. Turbulence also plays a role. Gas in the interstellar medium does not sit still. Supernova explosions, stellar winds, and gravitational instabilities all inject energy, creating chaotic motions. Turbulence naturally generates structure across a wide range of scales, from the size of entire clouds down to the smallest eddies. The sheet-like structures might channel gas flows. Stars form when gas collapses under gravity. If sheets direct how gas moves, they could influence where stars form. Regions where sheets intersect or compress might become preferential sites for star formation. Understanding these structures helps predict the future evolution of the galaxy. The observations also constrain theoretical models of turbulence in magnetized plasmas. Simulations predict how turbulent energy cascades from large scales to small scales. The observed structure size and orientation provide benchmarks for testing these simulations. When models match observations, It validates our understanding of the physics involved. Webb's ability to probe such fine structure demonstrates the power of infrared astronomy. Visible light is scattered and absorbed by dust, making dense regions opaque. Infrared light penetrates the dust, revealing what lies within. By observing at wavelengths where dust is transparent, Webb sees structures that visible light telescopes cannot. The light echo technique will be applied to other regions. Each supernova or bright transient event illuminates a different volume of interstellar space. By observing multiple light echoes, astronomers can map the three-dimensional structure of the interstellar medium across the galaxy. This creates a comprehensive picture of how matter distributes itself between stars. Knowing the structure matters for understanding star formation efficiency. If gas is organized into dense sheets, the collapse process might proceed differently than in smooth clouds. Sheets might fragment into filaments, which then break up into individual star-forming cores. The hierarchy of structures determines how many stars form and what masses they have. And just as Webb reveals hidden structures in nearby space, it continues discovering new methods to understand the cosmos. Measuring cosmic distances is one of astronomy's greatest challenges. For nearby stars, parallax works. Observe a star from opposite sides of Earth's orbit, and the star appears to shift position slightly against the background. The amount of shift reveals the distance. But this method fails for distant objects. The shifts become too small to measure. For more distant objects, astronomers use standard candles. These are objects with known intrinsic brightness. By measuring how bright they appear, you can calculate their distance. Cepheid variable stars serve as standard candles for nearby galaxies. These pulsating stars have a relationship between their pulsation period and luminosity. Measure the period, and you know the true brightness. Supernovae provide another standard candle for even greater distances. Type Ia supernovae have remarkably consistent peak brightness. They occur when a white dwarf star accumulates matter from a companion until it reaches a critical mass and explodes. The explosion releases a predictable amount of energy, making the supernova a reliable distance indicator. Webb has validated another technique using stars on the tip of the red giant branch. Low-mass stars swell into red giants late in their lives. As they ascend the red giant branch, their brightness increases. Eventually, they reach a maximum brightness and go no brighter. This maximum is called the tip of the red giant branch, and it occurs at a consistent luminosity. By identifying red giant branch stars in a distant galaxy and finding the brightest ones, astronomers can determine how far away the galaxy is. Webb's infrared sensitivity makes it ideal for this technique. Red giants emit strongly in the infrared, and Webb can detect individual stars in galaxies tens of millions of light-years away. A newer method uses carbon stars. These are evolved stars whose atmospheres are enriched in carbon. Carbon stars have consistent colors and brightnesses in the near-infrared spectrum. They serve as another type of standard candle. Webb observations have applied this method to measure distances to nearby galaxies. Using three independent methods together provides a powerful cross-check. If all three methods give the same answer for a galaxy's distance, you can be confident the measurement is accurate. A recent study used Cepheids, red giant branch stars, and carbon stars to measure distances to 10 galaxies. All three methods agreed, yielding a Hubble constant of 70 kilometers per second per megaparsec. This value falls between the two conflicting measurements that created the Hubble tension. It is lower than the value from supernovae, but higher than the value from the cosmic microwave background. This suggests the tension might be less severe than previously thought, or that the situation is more complex. The agreement between multiple methods also validates Webb's measurements. Some skeptics wondered if Webb might have systematic errors affecting distance estimates. By showing that three completely different techniques give consistent answers, the study demonstrates Webb's reliability. The telescope is measuring distances accurately. Refining the Hubble constant matters because it is a fundamental parameter describing the universe. It tells us the universe's age, size, and fate. An accurate value constrains cosmological models and helps predict future evolution. Every improvement in precision narrows the range of possible models. The carbon star method is relatively new. As astronomers gain more experience with it, they will refine the calibration and reduce uncertainties. Future Webb observations will measure distances to more galaxies, further improving the Hubble constant measurement. Combined with measurements at other wavelengths and with other techniques, a consistent picture should eventually emerge. But distance measurements are just one tool for understanding the universe. Webb continues to reveal how cosmic structures form and evolve over billions of years. The black hole does not just pull matter inward, it also blasts energy outward. As gas spirals into the event horizon, friction heats it to millions of degrees. This superheated material radiates intense energy across the electromagnetic spectrum. The pressure from this radiation pushes against surrounding gas, creating powerful winds that flow away from the black hole at thousands of kilometers per second. These winds reshape entire galaxies. When a supermassive black hole feeds actively, the outflowing winds can sweep through the host galaxy, pushing gas out of star-forming regions. Without gas, new stars cannot form. The galaxy's star formation shuts down. This process, called feedback, is one of the most important mechanisms governing galaxy evolution. Webb observations reveal feedback in action in the early universe. Galaxies with overmassive black holes show signs of powerful outflows. Spectra display emission lines with distinct shapes indicating gas moving away from the galaxy center at extreme velocities. The fastest outflows reach 3,000 kilometers per second, fast enough to escape the galaxy's gravitational pull entirely. This explains why early galaxies with massive black holes remain small. The black hole turns on first, consuming gas and growing rapidly. As it feeds, it generates tremendous energy output. This energy drives winds that prevent the surrounding galaxy from forming many stars. The black hole essentially stunts its host galaxy's growth. Eventually, the black hole exhausts the available gas supply. The accretion rate drops, and the energy output decreases. The winds weaken. Gas can now cool and collapse to form stars. The galaxy enters a period of rapid star formation, building up its stellar mass. Over hundreds of millions of years, the galaxy grows until the black hole to stellar mass ratio approaches the values we see in the local universe. This sequence explains the overmassive black holes Webb discovered. We are catching these systems during the first phase, when the black hole has grown large but the galaxy has not yet had time to catch up. Given another billion years, these galaxies would look more normal. The black holes would still be massive, but the stellar mass would have increased proportionally. Feedback also affects the surrounding intergalactic medium. Gas expelled from galaxies does not disappear. It flows into the space between galaxies, enriching the intergalactic medium with heavy elements created inside stars. This enriched gas can later fall back into galaxies or feed star formation in other systems. The cycle of gas flowing in and out of galaxies connects the evolution of individual objects to the evolution of the entire cosmic web. Simulations of galaxy formation must include feedback to match observations. Early simulations that ignored black hole feedback predicted too many massive galaxies forming too early. Adding feedback physics brings the simulations into agreement with observations. The energy from black holes regulates galaxy growth across cosmic time. Webb is testing feedback models by observing galaxies at different stages of evolution. Some show active outflows, others show no signs of feedback. By comparing these systems, astronomers can determine what triggers feedback and how long it lasts. These observations will refine theoretical models and improve our understanding of how galaxies form. But even as black holes sculpt galaxies in the early universe, they were also clearing away the cosmic fog itself. After the Big Bang, the universe glowed, protons and electrons floated freely in a hot plasma that radiated light. As space expanded and cooled, the temperature dropped below 3,000 degrees. Electrons and protons combined to form neutral hydrogen atoms. The universe became transparent, but it also became dark. This period is called the Cosmic Dark Ages. No stars existed yet to light up the darkness. Neutral hydrogen filled all of space. This gas absorbs ultraviolet light efficiently, making the universe opaque at certain wavelengths. Any light trying to travel long distances would be absorbed by intervening hydrogen. Then the first stars ignited. Their intense ultraviolet radiation ionized the hydrogen around them, splitting atoms back into protons and electrons. Ionized hydrogen is transparent to ultraviolet light. Each star created a bubble of ionized gas expanding outward. As more stars formed, these bubbles grew and eventually merged. Within several 100 million years, the entire universe became ionized again. This transition from neutral to ionized is called reionization. It represents one of the major phase changes in cosmic history. Understanding when and how it happened reveals crucial information about the first stars and galaxies. Webb is designed specifically to study this epoch. The telescope observes galaxies from the reionization era at redshifts between 6 and 10. These galaxies existed when the universe was partially ionized. Some regions had been cleared by earlier stars. Other regions remain neutral. By studying these galaxies, astronomers can determine how many ionizing photons they produced and how fast reionization progressed. The challenge is that not all photons escape galaxies. Ultraviolet light can be absorbed by dust or neutral gas within the galaxy itself. Only photons that escape into intergalactic space contribute to reionization. Measuring the escape fraction is difficult but essential for understanding the process. Webb spectra reveal clues about escape fractions. Certain emission line ratios indicate whether ultraviolet photons are escaping or being absorbed internally. Galaxies with high escape fractions show specific spectral signatures. By identifying such galaxies, astronomers can estimate what fraction of early galaxies contributed significantly to reionization. Current observations suggest that most early galaxies have moderate to high escape fractions. This means they efficiently released ionizing photons into intergalactic space. Combined with the surprisingly large number of bright galaxies Webb has found, this suggests galaxies alone could have reionized the universe. Earlier theories proposed that exotic sources, like quasars or population 3 stars, dominated reionization. Webb data indicates ordinary star-forming galaxies did most of the work. The timeline of reionization remains uncertain. Most evidence suggests the process completed by redshift 6, about 1 billion years after the Big Bang. But exactly when it started and how long it took are open questions. Did reionization happen quickly, in a few 100 million years, or did it proceed slowly over 1 billion years? Webb observations are constraining the timeline. By measuring the neutral hydrogen fraction at different redshifts, astronomers can map reionization progress. Early results indicate the process accelerated around redshift 8. Before that, progress was slow. After that, the remaining neutral hydrogen disappeared rapidly. One puzzle involves the topology of reionization. Did the ionized bubbles grow uniformly in all directions, or did they follow the cosmic web structure? Simulations predict that ionized regions should preferentially expand along filaments where galaxies cluster. Voids would remain neutral longer. Testing this requires mapping both the ionized regions and the galaxy distribution simultaneously. Webb is beginning to provide such maps. Large surveys image and obtain spectra of thousands of galaxies across wide areas of sky. Combined with measurements of the intergalactic medium's ionization state, these data reveal how reionization unfolded in 3 dimensions. The emerging picture shows a patchy, complex process that varied significantly from region to region. and some of the tools for studying reionization come from an unexpected source. Einstein's theory of general relativity predicts that mass warps spacetime. Light traveling through warped spacetime follows curved paths. When a massive object like a galaxy cluster sits between us and a more distant galaxy, the cluster's gravity bends the light from the background galaxy. This bending can magnify the background object, making it appear brighter and larger than it would without the lensing. Astronomers call this gravitational lensing. It acts like a natural telescope, magnifying distant objects that would otherwise be too faint to study. Webb exploits gravitational lensing systematically to observe the faintest galaxies in the early universe. By pointing at massive galaxy clusters, the telescope gains access to galaxies behind them that are magnified by factors of 10 or even 100. One recent observation targeted a cluster called Abell S 1063. This massive collection of galaxies sits 4.5 billion light-years away. Its gravitational field distorts the images of more distant galaxies into arcs and multiple images. Webb captured hundreds of such distorted background galaxies in a single image. Some of these lensed galaxies date back to when the universe was less than 1 billion years old. Without the magnification from the cluster, they would be completely undetectable. Even with Webb's power, the unaided view would show nothing. The gravitational lens makes the impossible possible. Lensing also allows detailed study of individual galaxies. When a galaxy is magnified by a factor of 50, features that would normally be too small to resolve become visible. Astronomers can study the distribution of star formation within the galaxy, identify individual star clusters, and measure properties that would otherwise require much larger telescopes. One lensed galaxy observed by Webb shows 10 distinct star clusters. Each cluster represents a region where stars formed simultaneously from a collapsing gas cloud. The clusters have different ages, indicating that star formation occurred in multiple bursts rather than continuously. This level of detail is only accessible because gravitational lensing magnified the galaxy enough to resolve its internal structure. The amount of magnification depends on the alignment. If the background galaxy sits directly behind the center of the lensing cluster, the magnification can be extreme. Slight misalignments produce less magnification, but still help significantly. Astronomers model the cluster's mass distribution to calculate the exact magnification factor for each background object. Gravitational lensing also reveals information about the lens itself. The distortion pattern depends on how mass distributes in the cluster. By analyzing the shapes and positions of lensed galaxies, astronomers can map the cluster's total mass, including its dark matter. This provides an independent measurement of dark matter properties. Some clusters produce multiple images of the same background galaxy. Light from the galaxy takes different paths around the cluster, arriving at Earth at slightly different times and from different directions. Astronomers see the same galaxy in 2, 3, or even more positions in the sky. By comparing these images, they can test general relativity and constrain the cluster's mass distribution with high precision. Webb has observed dozens of massive clusters as gravitational lenses. Each observation reveals hundreds of lensed background galaxies. The cumulative result is a dataset of thousands of extremely distant galaxies, many magnified enough for detailed study. This sample is revolutionizing our understanding of galaxy formation in the first billion years. One particularly powerful application combines lensing with spectroscopy. Webb obtains spectra of lensed galaxies, measuring their chemical composition, star formation rate, and ionization state. The magnification makes it possible to study galaxies that would be far too faint for spectroscopy without lensing. These measurements provide unprecedented insight into the properties of typical galaxies during reionization, and some of the lensed galaxies show unexpected characteristics. The galaxy appeared as an elongated arc in Webb images of a massive galaxy cluster. Gravitational lensing had stretched and magnified it. Astronomers nicknamed it the Firefly Sparkle because of its appearance. When they examined it closely, they found something remarkable. The galaxy contained 10 distinct, bright star clusters, each clearly resolved in Webb's images. This galaxy existed about 600 million years after the Big Bang. At that time, the universe was less than 5% of its current age. Most galaxies observed at this epoch appear as single, compact blobs. Firefly Sparkle showed clear internal structure. The star clusters stood out as individual bright points arranged in a line. Measuring the properties of each cluster revealed that they have different ages and masses. Some contain young, hot stars just a few million years old. Others have slightly older populations. The clusters range from a few thousand to several 100,000 solar masses. Together, they total about 10 million solar masses of stars. This total stellar mass is surprisingly low for a galaxy. The Milky Way contains over 100 billion solar masses of stars. Firefly Sparkle has less than 1/10,000th of that. Yet this lightweight galaxy might resemble what the Milky Way looked like at a similar age. Both the timing and the mass match predictions for our galaxy's early state. The discovery demonstrates that massive galaxies, like the Milky Way, built up gradually from much smaller systems. Firefly Sparkle is not a fully formed galaxy. It is a building block, a proto-galaxy in the process of assembling. Over billions of years, systems like this would merge with others, growing into the massive galaxies we see today. The 10 star clusters provide a snapshot of star formation in action. Each cluster formed from a collapsing gas cloud. The fact that they have different ages shows that star formation did not happen all at once. Instead, it occurred in bursts separated by millions of years. Gas accumulated in the galaxy, triggered star formation, and then perhaps blew out or heated up, pausing star formation until more gas arrived. This episodic star formation might be common in early galaxies. Gas flows into the galaxy along cosmic web filaments irregularly. When gas arrives, it triggers a burst of star formation. Feedback from the newly formed stars then heats the gas and prevents further star formation temporarily. The cycle repeats each time new gas accumulates. Without gravitational lensing, Firefly Sparkle would have been impossible to study in detail. The magnification factor of about 30 made the galaxy bright enough for Webb to resolve individual star clusters. This demonstrates the power of combining gravitational lensing with Webb's capabilities. Together, they provide a microscope for examining the early universe. Other lensed galaxies show similar clustering of star formation. It appears that many early galaxies form stars in distinct regions rather than smoothly throughout their volume. This clumpy star formation might reflect the turbulent conditions in early galaxy gas reservoirs. Instabilities cause gas to fragment into dense clumps that each form a cluster of stars. The clusters themselves might be the precursors of globular clusters, ancient star clusters that orbit most large galaxies today. Globular clusters contain hundreds of thousands to millions of stars packed into spherical regions just a few dozen light-years across. Their ages indicate they formed in the early universe. Firefly Sparkle's star clusters have similar masses and might evolve into objects resembling the Milky Way's globular clusters. Studying galaxies like Firefly Sparkle connects the distant past to the present. By understanding how small protogalaxies assemble and form stars, astronomers learn how systems like the Milky Way came to be. We are seeing our own history written in the light from these ancient objects. Yet, even as galaxies build themselves from star clusters, the raw materials for planets and life were being forged. Stars form from collapsing clouds of gas and dust. The cloud flattens into a disk as it rotates. The star ignites at the center, and the disk surrounds it. This disk contains all the material that will eventually become planets, moons, asteroids, and comets. Understanding the disk's composition reveals what building blocks are available for planet formation. Webb observed a young stellar system and detected crystalline water ice in its disk. This form of ice has a regular molecular structure, like ice in a freezer. It differs from amorphous ice, where water molecules arrange randomly. The presence of crystalline ice indicates specific temperature and pressure conditions in the disk. The ice sits far from the central star, in the cold outer regions where temperatures drop below freezing. Webb's spectrum showed distinctive absorption features at specific infrared wavelengths that match crystalline water ice. The signal is unambiguous. The disk contains abundant ice in the region where giant planets might form. This discovery matters because water is essential for life as we know it. Rocky planets forming in the inner disk start out dry because temperatures are too high for ice to exist. Water must be delivered later, either by comets or asteroids that formed in the outer disk and then migrated inward. The ice web detected represents the reservoir that could eventually supply water to inner rocky worlds. Giant planets also require water ice. Current models suggest that Jupiter and Saturn formed when icy cores grew large enough to gravitationally capture surrounding hydrogen and helium. The cores built up from collisions of icy planetesimals, solid objects ranging from meters to hundreds of kilometers across. The abundant ice web detected provides exactly the material needed for this process. The crystalline structure tells us about the disk's history. Amorphous ice forms when water vapor freezes rapidly. Crystalline ice requires either slow freezing or a period of warming that allows molecules to rearrange. Finding crystalline ice suggests the disk has experienced thermal processing, perhaps from shock waves or radiation from the central star. The observations targeted a disk around a star similar to our home star. This makes the findings directly relevant to understanding solar system formation. If ice was abundant in the solar nebula, then the process Webb is observing might mirror what happened 4.6 billion years ago when our planetary system formed. Other disks, observed by Webb, show similar ice features. This suggests that crystalline water ice is common in planet-forming disks. Most planetary systems likely have access to substantial amounts of water during formation. This increases the probability that rocky planets in habitable zones could acquire water and potentially develop conditions suitable for life. The amount of ice matters as much as its presence. Too little ice, and giant planets might not form. Too much, and the disk might fragment into multiple cores that compete for material. Webb measurements of ice abundance in multiple disks will reveal whether there is a typical amount or if it varies widely from system to system. Beyond water ice, disks contain other ices. Carbon dioxide, methane, and ammonia all freeze at temperatures found in outer disk regions. Webb has detected these ices in some disks. The mix of different ices affects planet composition. A planet forming from ice-rich material will have a different chemistry than one forming from rock-rich material. These observations connect star formation to planet formation to astrobiology. The ices in planet-forming disks determine what raw materials are available. The planets that form inherit their compositions from the disk. Rocky planets in habitable zones might acquire water, atmospheres, and organic compounds. Some of those planets might eventually develop life. Webb is cataloging the ingredients across many stellar systems. By the end of its mission, astronomers will have a statistical understanding of how common different disk compositions are. This will constrain theories of planet formation and help predict what kinds of planetary systems exist throughout the galaxy. And while Webb studies the formation of new systems, it continues observing the deaths of old stars. The gamma-ray burst lasted 8 seconds. In that brief time, it released more energy than the home star will emit over its entire 10 billion year lifetime. The explosion hurled jets of material outward at 99.99% the speed of light. When one of these jets pointed toward Earth, detectors across the world recorded the flash. This particular burst came from the early universe. The gamma rays traveled for more than 13 billion years before reaching Earth. By the time Webb observed the afterglow, the explosion was already ancient history, yet the observation revealed details about stellar death during the first billion years of cosmic time. Gamma-ray bursts come in two types. Short bursts lasting less than 2 seconds originate from merging neutron stars. Long bursts lasting more than 2 seconds come from collapsing massive stars. The 8-second burst Webb studied clearly fell into the long category. This was a massive star dying. The mechanism involves core collapse. When a star more than 20 times heavier than our home star exhausts its nuclear fuel, the core can no longer support itself against gravity. It collapses to form a black hole. Material falling toward the black hole forms an accretion disk. Magnetic fields threading the disk launch jets perpendicular to the disk plane. These jets punch through the collapsing star, emerging from the stellar surface at relativistic speeds. The intense energy heats the jet material to billions of degrees, producing gamma rays. As the jet continues outward, it sweeps up surrounding material, creating a shock wave that radiates across the electromagnetic spectrum. Webb observed this burst at multiple wavelengths. The infrared spectrum showed emission lines characteristic of heavy elements. Silicon, oxygen, and iron appeared in the spectrum. These elements formed inside the dying star through nuclear fusion and were expelled during the explosion. Webb was analyzing the star's innards spread across space. Finding heavy elements in the spectrum indicates that even early universe stars produced them. This might seem obvious, but it was not guaranteed. Very low metallicity stars might die differently, perhaps without producing as many heavy elements. The fact that this ancient burst shows similar enrichment to modern supernovae suggests the underlying physics has not changed. Gamma-ray bursts also serve as probes of the intergalactic medium. Light from the burst passes through gas between the explosion and Earth. This intervening gas absorbs certain wavelengths, leaving imprints in the spectrum. By analyzing these absorption lines, astronomers can study the composition and density of intergalactic gas billions of years ago. The observations revealed neutral hydrogen absorption, indicating the burst occurred during or near the end of reionization. Some neutral hydrogen still existed along the line of sight. This constrains when and where reionization completed. Different lines of sight to different gamma-ray bursts will map the patchiness of reionization across the sky. Gamma-ray bursts are rare, only about 1 per galaxy every million years. But in the observable universe, hundreds occur every day. The challenge is catching them quickly and observing before the afterglow fades. Ground-based telescopes can alert Webb within minutes of a detection, triggering rapid observations. These rapid response observations capitalize on Webb's flexibility. The telescope can interrupt scheduled programs to observe transient events. For gamma-ray bursts, speed is essential. The afterglow fades rapidly, dropping to undetectable levels within days. Webb must observe within hours to capture useful data. Each gamma-ray burst observed at high redshift adds to our understanding of massive star death in the early universe. The sample is growing. Within a few years, Webb will have observed dozens of distant bursts, providing statistics on their properties and surrounding environments. This will reveal how the deaths of the first massive stars enriched the cosmos and triggered subsequent generations of star formation. But the discoveries continue pushing deeper into time. Every few months, astronomers announce a new distance record. The most distant galaxy known keeps getting more distant. Each new record holder existed earlier in cosmic history, closer to the Big Bang. The progression shows Webb pushing the frontier of observable time steadily backward. JWST held the record at redshift 14.32 for several months. Then, another galaxy was confirmed at redshift 14.5. A few months later, a candidate appeared at redshift 16. Spectroscopic confirmation is pending. If real, this galaxy formed just 250 million years after the Big Bang. Why does the record keep advancing? Partly because Webb is still young. Astronomers are analyzing data from its first few years of operation. As they work through the observations, they find fainter and more distant objects. The deepest images require tens of hours of exposure time. Not all deep fields have been observed yet. More are scheduled. Advancing technology helps too. Analysis techniques improve as astronomers gain experience with Webb data. Machine learning algorithms scan images, identifying candidate high-redshift galaxies that humans might miss. Spectroscopic follow-up confirms or rejects these candidates. The process is becoming more efficient. There is also statistical inevitability. If bright galaxies exist at redshift 14, even brighter ones probably exist at redshift 15. Galaxies form continuously, and the earliest ones are simply the rarest. Search a large enough volume of space, and you will find them. Webb is searching that volume. The distance record cannot advance forever. Eventually, we reach the epoch of the first stars. Before redshift 20 or so, no stars existed. The universe was too young. Going beyond redshift 20 means looking at the dark ages, when only neutral hydrogen filled space. Webb might detect faint emission from this hydrogen, but it will not find galaxies. Between redshift 14 and 20 lies unexplored territory. Webb has found galaxies at 14. Theorists predict galaxies should form by redshift 15 or 16. The gap between prediction and observation is narrowing. Within the next few years, Webb will likely discover galaxies in this range, extending our view to cover 98% of cosmic history. Each record-breaking galaxy teaches us something. The brightness reveals star formation rates. The spectrum shows chemical composition. The size indicates how structure forms. Together, these measurements constrain models of galaxy formation. Each new galaxy either confirms predictions or forces revisions. Some early galaxies appear surprisingly ordinary. They form stars, contain some heavy elements, and have sizes consistent with models. Others are extreme outliers. Too bright, too massive, too enriched. These outliers are the most interesting because they challenge our understanding. They indicate physics we do not fully grasp. The record holders also grab public attention. People find it fascinating to see light from near the beginning of time. Images showing galaxies from the first few 100 million years make the abstract concept of cosmic history tangible. You are looking at photons that have traveled for 13 billion years to reach your eyes. But behind the distance records lies a deeper mystery about the universe itself. The universe is not just expanding, the expansion is accelerating. Galaxies are moving away from each other faster now than they were billions of years ago. Something is pushing space apart with increasing strength over time. Astronomers call this mysterious force dark energy. Dark energy was discovered in the late 1990s using observations of distant supernovae. By measuring how bright these explosions appeared, astronomers determined their distances. Comparing distance with redshift revealed that the expansion rate has been increasing. The universe was decelerating for the first several billion years, slowed by gravity pulling matter together. Then, about 6 billion years ago, dark energy began to dominate, and the expansion started accelerating. Webb observations confirm and refine these findings. By studying more supernovae at higher redshift, Webb extends the measurement of cosmic expansion history further back in time. The data show that dark energy has been present for billions of years, consistently causing acceleration. What is dark energy? Nobody knows. The simplest explanation is that it is a property of space itself. Einstein's equations allow for a cosmological constant, an energy density that remains the same as space expands. This means that as the universe grows, more dark energy appears because there is more space. The total energy increases, driving faster expansion. This sounds like it violates energy conservation. In a sense, it does. But general relativity allows this, because energy conservation works differently in curved spacetime. The expansion of space can create or destroy energy without violating the equations. Dark energy is one manifestation of this strange behavior. Measuring the properties of dark energy is a major goal of modern cosmology. Is it truly constant, or does it change over time? If it changes, The rate of change constrains theoretical models. Webb observations provide data points at different cosmic epochs, tracking how dark energy behaved over billions of years. Current measurements suggest dark energy has been remarkably constant. Its density does not appear to change significantly as the universe evolves. This matches the simplest models but leaves the fundamental nature of dark energy unexplained. A cosmological constant fits the data but does not tell us why it exists or why it has the specific value we measure. Alternative theories propose that dark energy is not a constant property of space, but a dynamic field that evolves. Some models predict that dark energy should be stronger or weaker at earlier times. Webb measurements will test these predictions. So far, no clear deviation from a constant has been detected. The future of the universe depends on dark energy. If it remains constant, the expansion will continue accelerating forever. Galaxies outside our local group will recede faster and faster, eventually moving away faster than light can travel toward us. They will disappear beyond the cosmic horizon, forever unreachable. The universe will become increasingly dark and empty as stars burn out and are not replaced. If dark energy increases over time, the acceleration could become so extreme that it tears apart galaxies, stars, and eventually atoms. This scenario, called the Big Rip, would destroy all structure in the universe. Current measurements give no indication this will happen, but the possibility exists. If dark energy decreases, the expansion might eventually reverse. Gravity would take over, pulling everything back together in a big crunch. The universe would collapse to a singularity, potentially followed by a new Big Bang. This cyclic model is speculative and not favored by current data. Webb contributes to dark energy studies by providing precise measurements of cosmic expansion at different times. These measurements, combined with data from other telescopes and experiments, will eventually reveal whether dark energy is truly constant or evolves. Understanding dark energy is one of the deepest questions in physics. Yet, even with all of Webb's power, there are limits. Webb is the most powerful telescope ever built, but it cannot see everything. There are limits. Some objects are too faint, some are too distant, some emit light at wavelengths Webb cannot detect. The first 200 million years after the Big Bang remain largely hidden, just beyond the edge of what Webb can reach. Galaxies from this earliest epoch would have redshifts above 20. Their light has been stretched so far into the infrared that even Webb struggles to detect them. The galaxies would also be small and faint, having had less time to form stars. Detecting them requires extremely long exposures and possibly gravitational lensing to provide magnification. Webb has the technical capability to find galaxies at redshift 20 if they are bright enough, but brightness depends on star formation rate and mass. Early simulations predicted the first galaxies would be tiny, with masses of just a few million solar masses. Such objects would be far too faint for Webb to detect without extraordinary lensing. However, if the first galaxies formed stars more efficiently than models predict, they might be bright enough to see. This is plausible given that early galaxies have consistently been brighter than expected. If the trend continues to earlier times, galaxies at redshift 20 might be detectable after all. Another challenge involves contamination. At these extreme redshifts, distinguishing real high redshift galaxies from other objects becomes difficult. Certain types of cool stars in our own galaxy can mimic the colors of distant galaxies. Spectroscopy can differentiate them, but obtaining spectra of the faintest candidates requires enormous amounts of telescope time. The James Webb Telescope will operate for at least 10 years, possibly longer if fuel reserves and instruments remain functional. During its lifetime, it will conduct deeper and deeper observations, pushing closer to the epoch of the first stars. Future telescopes might eventually peer beyond Webb's reach, but for now, it represents the frontier. What could surpass Webb? Larger ground-based telescopes with adaptive optics are under construction. These will have greater light-collecting power in some wavelengths. However, Earth's atmosphere absorbs much infrared light, limiting ground-based infrared astronomy. For the most distant galaxies, space-based infrared telescopes remain essential. The next generation of space telescopes is still being planned. Concepts include telescopes with mirrors twice the size of Webb's or arrays of telescopes working together. These facilities would extend observations to redshift 25 or beyond, potentially imaging the very first stars. But they will not launch for decades. In the meantime, Webb is transforming our understanding of the cosmos. Every observation reveals something unexpected. Black holes too massive for their galaxies, galaxies too bright for their age. Star formation proceeding differently than models predicted. Structures emerging earlier than thought possible. These discoveries do not break cosmology, they expand it. Our models were too simple, our predictions too conservative. The universe is richer and more complex than we imagined. Webb shows us the reality, and our theories must adapt to match. We are living through a golden age of astronomy. Never before have we seen the early universe so clearly. Never before have we watched galaxies forming just after the Big Bang. Never before have we probed the depths of stars billions of light years away, or examined the internal structures of distant stellar nurseries. James Webb has uncovered the true scale of the universe, and it is vaster, stranger, and more magnificent than anyone predicted. Every week brings new discoveries.